we've got a couple things to talk about before we actually get into the class. So before we go into the lecture proper, I just want to give you a very quick overview of the LMS. By now, I trust that all of you have actually seen this, but I want to show you one or two things just for your enjoyment and so that you can access the resources you need. So one thing, probably one of the key things I want to point out, especially for you, those of you already on Zoom, is this button right here, Access Zoom Lectures. If you click that button, Liam here has actually written this beautiful script that will take you to today's lecture. So instead of having to go into the Zoom button and figure out which day it is, just press that button. We also have access to Grok, which is the toolkit that you'll be using to access all the activities and assignments throughout the week. And through the workshops. Many of you have seen this in Foundations of Computing, but for those of you who've come through the programming proficiency test, this is where all your coding exercises are going to be. We have Ed, and let me actually click through. This is going to be our announcement mechanism and our Q&A, as you can see here. And we already have someone asking, where is the lecture link? This is why we took an extra minute to start. Unfortunately, the Zoom link on the actual Zoom page wasn't quite working. So glad to see that we have fixed that up. Back to the LMS for a second. If I can, this computer will actually respond. I've tried to keep all the core links for the class available on the home page. I will likely keep this little bar over here updated with announcements throughout the semester and key things. You can already see that this has changed to a link to lecture 1 in 4K ultra high definition, which if any of you want to recap the material, instead of going to the lecture capture, I encourage you to check out this YouTube link. Let's go to it just for a second on actual YouTube, and you'll be able to see, once it loads, that there are convenient chapter markers. So you can see class policies, getting help, giving feedback, academic honesty, et cetera, assessment. This should be a really enjoyable way for you to recap the material in the instances where I've been able to do a more professional recorded version of the lecture. We do have a student-operated chat button here. This is an invite link to Discord. I think it might need to be updated, but for those of you who want a space that's not moderated by me and the other teaching staff to chat about the class, this is one particular venue. Perhaps there's another Discord that I don't know about, but this is the one that I do. We also have a link to the tutorials. You can see the staff, etc. Explore the LMS, click each of the links, and with that, we will move back to some of the subject material. So you'll remember from yesterday that we had this problem. How do we efficiently find repeated sequences of letters in a large text? Remember, for the purposes of this exercise, the text is going to be quite large and the repeats are going to be quite short. This fact will become increasingly important as we continue our analysis. So we might be looking for repeats of, say, size 7 or size 3 or size 4, but our text is going to be large, maybe the text of Moby Dick. Thank you very much. And we want to find an efficient way to do it. This was our example from yesterday. A few of you pointed out that I was missing dots at the end of @.rat. And that was actually 6 letters long. So that is now corrected. And this was our algorithm. And remember, we got part of the way through understanding it, but it was still pretty confusing. And so now we're going to continue to do a worked example of it and see how this works. So we have our string, fat.rat.eat.bat, etc., etc. And we want to find repeated sequences in this. We have one pointer I that loops all the way through the array, leaving space at the very end to make sure that we don't overflow when we're checking for repeats that are 7 letters in length. We have a second pointer in J, J as well. And we're going to use these 2 pointers to determine where the repeats are. The way this will work is I will start at the start of one sequence, and J will pick another starting point. And if we compare the 7 letters starting at I and the 7 letters starting at J, if the 2 of them match, we know there's a repeat. Again, if we start at I and we look at the first letter starting at I, and we look at the first letter starting at J, and they're the same, we've found the start of a match. Then we look at the next letter next to I and the next letter next to J. Are they the same? If so, it's still possible that we've got a match. And we keep doing this until we've checked M characters, because M is the length of the repeat that we're looking for. So the way this would work is for each possible starting place of a repeat. So the first possible starting place is for I is obviously at the very beginning of the string. We want to see if there are any repeats of the first 7 letters. So J moves along, checking, checking, checking. And so the first sequence of letters that we check is @.r. Does @.r, oh, this is repeats of length 3 in this case, to make it a little simpler for us to see. So does @.r match fat? Yes, no, doesn't match. So we move on to t.r. T.r doesn't match either. Neither does .ra, etc., until we get all the way to fat. Over here. And so when J gets to this point, when J is now at, when J is at fat dot, the 2 will match and we've found a possible repeat. Now, when I moves along 1, and now I is starting at dot. We do the same process again. J moves along in this direction. And when it gets to @dot over here, when J is here, the 2 comparisons match up and we've found another repeat. And this works fine on our nice small string that we've got. But how about on bigger strings? Is this still going to be functional? Let's take a look and actually find out. So now we're going to today take a look at actually running this program in the terminal. And thanks to our advances in technology since yesterday, it is now working. So in this directory, which I enumerate the contents of with this command ls, we'll talk more about how to navigate through directories in your terminal later, I have a whole bunch of different programs and files. One of the programs is conveniently find repeats 0, the program that we were talking about. And we can feed in both the length of the repeats we want and our test text, which was this fat.rat. You can see it's producing the output we expected. And that was pretty fast. In fact, we can find out just how fast by using the time command to time something in our terminal. Let's see what happens. It took almost no time at all, 0 seconds, 0.006 seconds total. Blazingly fast. Okay, that works for our small string. What about with a larger string? So here I have, I think this is War and Peace. I have the first 1,000 characters of War and Peace. Does that run quickly? Yeah, a little slower, 0.012 of a second, but still reasonable. Now what happens if I make it larger again? Okay, that's not so fast anymore. That was 1.4 seconds, and I can keep making this larger and larger. And the time's going to grow and grow and grow until the point where this is no longer very efficient. It's not actually solving the problem in a reasonable amount of time. So that was not that long, but we can keep adding zeros and make the problem bigger and bigger and bigger. And of course, we're all familiar now with the size of various platforms on the internet. If you wanted to run this across everyone's posts on Facebook, it would take far, far too long for this to produce actually usable information for you if you're trying to run this algorithm on your large data set. So we're going to need a way of improving our initial find repeat 0 so that it's more efficient and can actually solve some of the larger challenges that we experience. And I'm just going to leave that running. One of the big questions that we're going to ask over and over in this course is how much extra memory do we need and how much extra time do we need as the input gets bigger? So as we move from fat.rat. etc. to War and Peace, the 1,000 characters, how much extra do we need? What about when we go to 100,000? What about when we go to 1,000,000? Is there a way to quantify the change in memory that we need and the change in time that we need in proportion to the growth in our input? So if our input doubles, what would be the growth in the amount of time that it takes? If our input quadruples, what would be the amount of time that it takes? And now you can see where the math is starting to come into this. For example, does the amount of time grow? Do you get a squared increase in the amount of time it takes? Do you get a cubic function of the amount of time you've added? Or maybe something different? Our essential question here is for every n units of growth in the size of the input. So if we've gone from 1 to 10, in this case, n would have gone up by 9, with our total n being 10. For every n units of growth in the input size, by what proportion do our needs for our resources grow? The way we represent this is using something called big O notation. And while in this course we're not going to give you too many of the details of it, you should at least have a basic familiarity with this descriptive form of growth by the end. This is called asymptotic analysis. Why asymptotic? Because we don't care really about the change between an input of size 3 and input of size 4. What we care about is the behavior of the algorithm writ large. Like if we double our input or if we make our input 10 times, by what proportion do things grow? Why do we care about it in this way and not in the other way? Well, one way of thinking about it is that everyone's computer is different. So a program that I run on my 2016 MacBook might take 3 seconds, but on Liam's M1 Mac, it might actually take 1 second. But the important thing is not the exact number of seconds that the program takes to run in most cases. It's the way in which it changes in response to growths in the input. So for example, if we're talking about a doubling factor, mine will take 6 seconds while Liam's takes 2. But as that gets bigger and bigger and bigger, those differences will start to mean less. It'll be the order of magnitude that takes precedence and the growth behavior of the function. So this is what we mean by asymptotic analysis. And these are some examples of different forms of growth that you might have. So for example, your function might grow the amount of time it takes to run your function might grow pretty slowly as the size of your input grows. That would be, for example, square root of n growth. So if you double this, if you say quadruple the size of your input, you will only double the size of the amount of time that it takes because the square root of 4 is 2. Then at the top, which we can't really see thanks to the zoom there, I'll move that bar. If you might have, for every 1 unit of growth of your input, you might have roughly 1 unit of growth of your amount of time that it takes. And then at the top end, we've got things like it's squares. For everything for every doubling, it takes 4 times as long. Or 2 to the n for every, that's called exponential growth. If you double it, you'll get a 4 times increase in the amount of time, and so on and so forth. We'll go through some of those a bit later. So let's see if we can actually measure this with our program. This took 1 minute and 26 seconds to run it at 1 million. And let's see, 40,000. And that took 1.4 seconds. So we can see that it is observing one of these larger kinds of growth categories in this particular case. But it's one thing to be able to run it and plot the different amounts of time that it takes for different inputs. But that is a fairly coarse tool. And obviously, we don't really have enough time every time we write an algorithm to run all these experiments. A better way of doing it would be maybe, what if we can mathematically analyze it and actually do a calculation that yields this form of behavior? So let's go back to our algorithm and see if we can do that. What does the amount of time taken to run our at.fat.repeats function, what does it depend on? And we'll go to the audience for this one. What determines how long this function takes? Liam, do you have the audience thing? Yeah, anyone in the audience or on Zoom? Yeah. So we'll pass the microphone around for next time. We'll run it up and down. But for now, remind me your name again. Jacob. I knew it started with a J. The amount of time that it takes is going to depend on the amount of characters that we're searching through. But it might also depend on the size of the length of the repeats that we're looking for as well. Which of these is going to be the predominating factor? Can any of you tell? Is it going to be more dependent on the size of the overall text on the War and Peace thing? Or is it going to be more dependent on the size of the repeats? Back there. And say your name into the microphone as well.
Yash.
Anyone who says size of the text? Okay, we've got a couple people here. Liam, run the microphone down. One of you are going to explain why you think it might be the size of the text. Okay, hands up. Why, for someone who said it was the size of the text?
Because as the text gets larger, the
Liam.
more text has to be processed through the function, and the time will increase.
Oh, we've got a bit of interference coming through here. I'll try and... Doesn't look like there's going to be a way to fix that. Yes. So let's actually do our analysis and see. So I'll leave our algorithm over there, and we're going to actually work it out on the iPad. So our outer loop, how many times did our outer loop run? How many times did we iterate through I at the start? How many different places could I go through? If the size of the text is n and the number of repeats is m, what was the bounds on the outer loop? Who remembers? It was just shown on the slide. Yara, say louder. N minus m, that's correct. So that's the first thing we do. N minus m times, we're going to increment our variable I. What about the inner loop? How many times did the inner loop run? So you might not remember it, but that's okay. But it was going to run each time a little less because it's going from where I is forwards across the end of the string. So if I is already at the 5th last position, J is going to start at the 4th last position and keep going forwards. So each time it's going to get smaller. So it'll be n minus m minus 1 because it starts one place further along from I. And assuming that we fix n minus m, the next time it's going to have n minus m minus 2 because we've already moved I along one place, and now we have one fewer place for J to go. And we're going to keep doing this n minus m minus 3, n minus m minus 4. And then at each of those positions, we're going to have to check m characters. So if we're looking for a repeat of length 3, for each time that we fix I in one place and fix J in one place, we are then going to look 3 characters along for both of them. And we could even do 2m if you wanted to, because you're going to check for both of them. But we're just going to ignore it because we're interested in this case in the overall behavior of the algorithms, and we don't care about whether it takes 1 or 2 seconds. We want to know proportional to the inputs how long this is going to take. So now let's do our crunching. We have this mathematical identity that if we have a sequence that goes x minus 1 plus x minus 2, et cetera, we can boil that down to this expression here. So plugging, let's get rid of our circle. Plugging n minus m into that sequence, we get this expression. And then a whole bunch of math later, we're going to multiply this all out. So what we're doing here, we're taking our, we're taking this, and n minus m times this times m, and you'll see here, n minus m times that times m, and run it through, chug away. And this is the expression we get. Half mn squared multiply plus, I think there might be a missing plus sign there. Yes, there is a missing plus sign. Plus that thing multiplied by n, and then some expression at the end. And who can see what kind of form this is taking? What kind of mathematical expression is this? Yeah, it's a quadratic. And it's quadratic in which variable? In n. So m appears here as a cubic, so we could either say that this is cubic in m or cubic in n. And which of these two numbers is bigger for any given time that we run the program? N is bigger. Remember, that's like the size of our overall text. So which of these expressions, which of the things separated by pluses is going to be largest? So if I have to ask you, is m squared on 2 larger, or is a half mn squared larger? Which of those is larger? Half mn squared is larger because we already know that n is much, much larger than m. So we know that that term at the front is our biggest term. That's going to be the one that once we've put in reasonable values for m and n is going to be the one that dominates. And so what we do is we call this big O of n squared. We're dropping all the terms that don't matter because they have a small impact. And we can say that as the size of the input grows, the amount of time that it takes to run our program is going to be a square of the input. Exactly what is not going to be relevant to this analysis. What we want to do is just describe the overall behavior of this growth. And it turns out that for the find repeats 0 that we displayed, it's going to be roughly squared. This is pretty much as we saw before. We get something proportional to n squared m, which is going to be big O of n squared. Now we can actually look at the raw computer instructions that are operating here. So this is behind the hood. Once you implement this algorithm, if we look at the underlying computer code, at the instructions that the computer is actually running, this is how many instructions a comparison actually takes. A comparison between two things is not just one thing for the computer to do. If I tell you to compare two pictures, for example, you're going to look at the top line of the picture and both of them. As a human, you might look at the second line of the picture. You're going to do a bunch of steps before you're actually convinced that the two pictures are the same. Likewise, in order for a computer to compare two different things, it has to do a number of different steps. It puts them both in memory, it runs both things through a particular portion of the computer's circuitry, it then checks the results of the circuitry and reports it back. So when we say that it takes this many steps, well, you can always boil it down a little further and look at it under the hood. And part of the point of doing big O analysis, this asymptotic analysis, is not to care about this. So you don't have to peek under the hood and know exactly how many instructions it takes for the computer to do a comparison. But just for reference, it takes about 10. Wrapping this all up and putting together our big O expression with our knowledge of how many instructions it actually takes to do a comparison. When n is 1,000 and m equals 10, so our text is 1,000 characters long, and the number of repeats we're looking for is 10, then n squared m, which was this expression that we got out the other end, is roughly 10 to the 7. My laptop can do 10 to the 7 comparisons. My laptop can do about 10 to the 10 in comparisons per second. So you take these two numbers. The reason I'm doing 10 to the 8 there is because we know each comparison takes 10 instructions. So 10 to the 8 on 10 to the 10 yields 1,000th of a second. And if we were to check this in the terminal, you'd see that this calculation actually gives us the correct answer. Another question you might ask is, why do we care about this? What happens as every year passes?
Computers get faster.
Yes, computers get faster. So, if this program is big today, maybe it won't be big tomorrow. In fact, roughly every 18 months, we have something called Moore's Law that impacts the speed of computers. We get a rough doubling in the processing speed of computers and of the density of transistors, which are the switching elements on the processing units of the computer. But why might I have shown this video? Does Moore's Law still function today? No, we've started to lose some of these month-on-month gains, and computers won't be able to increase their processing power at this rate. Certainly not large enough to catch up with, remind me your name again? To catch up with Albert's view that our data sets are getting larger and larger. So our data sets are getting larger and our algorithmic needs are getting larger than the increase in speed of computers. And so this whole notion of efficiency becomes increasingly important and plays a real role in your day-to-day experience as computer scientists or as programmers. Even with Moore's Law, to match the size of the data increase from like our smallest War and Peace to our largest War and Peace, we'd have to wait 20 years. So even if we say that Moore's Law is going to keep happening and we keep finding scientific progress, we'll still always have a need for increases in the quality and efficiency of our algorithms. So what happens if we stop comparing if all m characters are the same? What change could we make to the algorithm by crossing out this line that would improve the efficiency of our algorithm?
We could immediately stop comparing when we find two characters that don't match and move on to the, I guess, to the other set of characters.
That's 100% correct. We don't actually need to compare all m characters to know when something's not a match. We only need to compare all m characters when we know that it is a match. So for most of the time, most things aren't matches. So most of the time, we won't actually have to do m comparisons. But yes?
Is that called short-circuiting?
One way of describing it might be short-circuiting. I'm not sure if that's always the term, but it's certainly one way that you could definitely refer to it. And so in the average case, we're not going to do m comparisons. We might only do one comparison. But what does this mean for our asymptotic analysis? Does it change much? If we go back a little bit and go back to here, n squared m, does the m really impact the overall behavior of the algorithm? Not in an asymptotic sense. It will improve on a day-to-day basis. If you're running this, you will see speed improvements. But if we're talking about data sets getting larger and larger by orders of magnitude, this average case is not going to help us very much. So this is the algorithm that Yara proposed. And what was your name again? Xinjiang. And that Xinjiang recommended we engage in a process of short-circuiting with our algorithms where possible. Early termination, finishing bits of our algorithm that don't need to keep running as early as we can. So as soon as any discrepancy is noticed, stop the algorithm running. This is actually much faster when you run it, but still n squared m in the worst case, assuming that someone has constructed a perfectly mismatched set of strings such that for every time you check, they've got an as closely matching as possible, except the very last letter is wrong. And then you get as close as possible to matching, but the very last letter is wrong. So if someone's being malicious and gives you a bad input, this can still be really bad. It's just that the average case is improved. And this is an introduction to a different form of analysis than just worst case asymptotic analysis that we were doing before. Turns out that average case and best case matter as well. And as we go through the course, we'll repeat this analysis on a number of different algorithms. What will happen in the best case where someone has thought, oh, I bet you they're going to use this algorithm to solve the problem, and they've given us the best possible version of our input. And we'll also look at what happens if that person is malicious and tries to give us the worst possible input. So on average, as we discussed, we only have to check k letters, and k is going to be much smaller than m, so faster, but not fast enough. When n is 1,000,000, we're still going to need at least 10 to the 12 comparisons, and that's at least 1,000 seconds. So hasn't helped with our grand scheme of finding all the repeats in all of War and Peace. And this is why we care about computer science, and this is what it means for all of you to be transitioning from people who might know how to program a little to computer scientists. You're studying the fundamental nature of programs and the fundamental nature of mathematics and the way that computers work within those constraints. It teaches us something more interesting about the world rather than just how to get a task done, because there are fundamental limits to the efficiency with which you can perform certain kinds of tasks. And one of the many jobs of a computer scientist is to figure out these limits and then to combine that with an understanding of the way that computers are designed to come up with efficient ways of actually implementing those solutions. One theme that we're going to come back to again and again and again as computer scientists is something that we call, pun intended, the space-time trade-off. And we have a beautiful example here of a wormhole to illustrate that. And the whole idea here is that there is going to be a trade-off between the amount of memory that an algorithm uses and the speed at which it can perform some of these tasks. This is not true for any algorithm, but we'll find in many, many, many cases that in return for sacrificing a bit of memory, we can actually change the asymptotic growth behavior of a particular algorithm. Perhaps by building some kind of large structure in our computer's memory, we can find an efficient way to go through that structure and solve a problem really quickly. Another way of describing this is that we do pre-computation. Before we actually go to solve an individual instance of a problem, we can do some work ahead of time that makes solving that problem easier. And this is particularly powerful in an instance when might it make a lot of sense to prepare for a problem ahead of time? And there'll be a few answers to this one. Liam, again, your name? Keith, okay. I'll put you on the Zoom.
Maybe when we're dealing with the same sort of data over and over again.
Yeah, and so what might an example of that be? Can you think of anything?
Like searching through the same text, maybe.
Exactly. So let's say we're doing this our repeats problem, and we're going to look for repeats of a few different lengths. Perhaps there's some way that we can do some work ahead of time that makes it just as easy to, or almost as easy to search for repeats of length 3 as repeats of length 4. So we do some work ahead of time, and then we go to find the individual repeats. It ends up much, much faster. The way we're going to do this is by developing something we call data structures. What these are is they're a way of thinking about the way we structure information and a corresponding way of storing that or representing it in a computer's memory. Now, these are an abstraction. What that means is that they're not real in a physical, tangible sense. For example, an Excel spreadsheet inside a computer is not a real thing, even while it's representing data in a tabular form. There is a physical analog of a spreadsheet, but the one inside the computer is there's not a physical spreadsheet that you can look inside the machine and find. The data structures describe a structured relationship between the different forms of data that are present within the data structure. And what time does this end? Oh, we don't have that long left. 10 minutes. Okay. So a prototypical example that I like to use here is files in folders. So if you go inside your computer's memory, there isn't actually a filing cabinet full of files and folders. We've chosen to represent data inside our computer through this hierarchical kind of tree relationship. So if I start at root and I'm looking for image 2, I start at the root, I know there's a folder called media, I go into media, and then I go into image 2. Now, this is both very efficient and very inefficient. What are some pros and cons of using a structure like this? Liam. Over here. And your name again?
I'm Bobby.
Bobby.
For the pros, when there's a lot of media, different sort of media, it can be easier for it to just be quantified, and then you can be able to access different files in different folders. But then the cons would be that if there's only little files in the folder, it takes a lot of effort compared to just being in the folder itself.
Yeah, so that's exactly correct. We have this trade-off between organization of things and structure, and the amount of time that it takes to find individual things if the folder is small. So if we have 100,000 files in a folder, going through all those 100,000 files is going to take a really long time. We'll have to do a lot of comparisons with the thing we're looking for. And so a structure like this would be much easier. Like, say we had 26 folders, one for each letter in the alphabet, and you could just go to the folder that represents the file you're looking for with the letter that it starts. Well, that would be much faster than looking through all 100,000. However, if you only have 5 files and you put all of them each in the separate folder, you're going to do a lot of extra clicks just to find individual files that you want. So the challenge here is to design the right tools, both the algorithm and the data structure that matches your problem. Pairing the right data structure with your problem could allow you to find large increases in the quality of your algorithm, and finding a better algorithm will give you inspiration for better data structures that you can use to similarly solve the problem. So this is the very first data structure of the class. This is called a suffix array, and it is called a, oh, I haven't been monitoring the chat very well. It's one of Liam's jobs. It's called a suffix array, because it gives all the possible suffixes for a given string. So up at number 1, if we start at index 1, the suffix starting at index 1 is the entire string, our entire test string. At index 2, it's all the letters remaining. At index 3, it's all the letters remaining from position 3. At index 4, it's all the letters remaining from position 4. And you'll note that in this case, I have 1 indexed this. I probably should have 0 indexed it, but take that under advisement. So this looks like something not that intelligent. How could this possibly help us solve the problem? Well, the data structure in this form doesn't help us that much, but, and my magic clicker move didn't work, but if we suddenly sort it, we're faced with a whole different kettle of fish. This is called lexicographic sorting. We're sorting it based on the letters with each suffix starts. And so there are a few things that we can say for sure about this process. So assuming that we've constructed it correctly, all possible suffixes in the string are present. Each suffix is matched to the place in the string where it starts. And the strings, this is really the key point, the string most similar to a string that you select is going to be on either side of it. Now, why might this be useful in helping us find repetitions? Think of that last point in particular. If we know that the string closest is on either side, Liam? Pass the microphone back.
If you know, like,
You're gonna have to shout.
It's only for Zoom.
because you know you're the string and you're trying to find a similar one, you only have to look at, or like it's easier to just look at the 2 nearest ones than to have to go through the whole
Yeah, so instead of checking out all possible suffixes, our solution is that we only have to check on either side to see if one of the 2 ones on either side is a repeat. So we've done a fair bit of work to make this structure, but now that we've made this structure, in order to find a repeat of any given string, we just look at the strings on either side of it. If neither of them are repeats or start with a repeat, then we know that there is no repeat for that particular substring. This is our new version of our find repeats algorithm. And we're not going to have time to finish going through it today, but the basic process is as follows. First, create the suffix array. So the way you do this is by going through all indexes of the string from 0 down to the end and putting all of them just like in that table. And that's what we're doing here. But you'll notice that instead of actually constructing the second side of the table, we're only constructing the left-hand side. We're putting all the indices in an array. Then do the sorting thing, but sort it based on the letters, based on the suffixes themselves. So just like we converted that array into this one, we're going to do the same thing just with our column. Once we've done that, our process for finding repeats is very simple. We compare at most m characters, just the same as before, but we do this only on either side of every string. So you'll see that we start at the top of our structure and we compare the first suffix with the next suffix. Is there a match? If yes, print it out, otherwise keep going. What about the second one? Does the second one match with the third one? If yes, print it out. If not, keep going. And we repeat this over and over and over until we have checked for each of the suffixes if it's repeating. And that's our algorithm. This makes finding one instance of a repeat very, very easy, and it only takes a slight modification to find all the possible repeats, which I'll leave to you as an exercise. And we will investigate the running time of this, as well as move to an introduction to the C programming language, which I know all of you are very, very excited for in our next lecture. Thank you very much, everyone, and I'll take any questions down at the front.